Okay, so in the previous section, we identified atomic isotopes, and in this section of the book, we're going to discuss atomic weights as well as formula weights and molecular weights. But to begin with, let's just review quickly the information that's given to us in the periodic table. So a given element is defined by the number of protons, right, which is given by the atomic number. That's up here, this top number. And below is another number that we call the atomic weight. Now, at this point, it turns out that the average mass of a single potassium atom is defined by this number in units of atomic mass units. First of all, what is an atomic mass unit? Well, here's the equivalency factor. One atomic mass unit is equal to this incredibly long string of integers times 10 to the minus 24th grams. Now, you might ask the question, how is it possible that we can weigh anything out to around 39 or so times 10 to the minus 24 grams? Because our scales, at very best, are good to 10 to the minus 5 grams. So that's a story that we're going to set aside for later, but it certainly is an interesting question. Now, this number reflects the average mass, meaning that if we took 100 potassium atoms, right, and we were able to weigh each one out individually, each one corresponds to potentially a different isotope, right? All of the atoms are going to have the same number of protons, 19, but they may vary in the number of electrically neutral neutrons. So, if we weighed out each of 100 individual potassium atoms and averaged them all together, this is the value that we would get, 39.0983 atomic mass units. All right, so that would be the average mass of a potassium atom. Now, this is a potential point of confusion and one that we're going to address later, but let's go ahead and bring it up now, is that it also turns out that this number, 39.0983, also expresses the mass of not a single potassium atom, but a huge number of them. Exactly, if you added up the masses of 6.022 times 10 to the 23rd atoms of potassium, and you added up all those weights, you would get 39.0983, but now the unit changes to grams, all right? Now this number of potassium atoms is called the mole. This is something that we'll again discuss in a later chapter in more detail, but I just want to bring it up right now that these numbers are the same, all right, and used to create a source of confusion, and that is historically we would say atomic weight to mean the mass of a single potassium atom, as well as the mass of 1 mole of them, which led to some confusion. We're no longer confused about this because we're addressing here the units, right? When we're talking about one atom, we use atomic mass units. When we're talking about a mole of atoms, this huge number of them, we talk about grams. Now, on the previous slide, we talked about the atomic weight and how to get atomic weight information from the periodic table, right? So in this case, we're going to look at how to calculate things called the molecular mass and the formula mass. It's probably easiest to do this by example. For example, if we take the formula CaCl2, right? What does this tell us? In our compound, we have 1 calcium and 2 chlorine atoms, right, in the formula. So if we want to get what's called the formula mass, which is just the sum of the atomic masses of each atom in the formula unit, we just take the mass of calcium and add it to the masses of 2 atoms of chlorine, right? So we just look these up in the periodic table. The atomic mass for calcium is 40.08 atomic mass units, and that for chlorine is 35.45 atomic mass units. We have 2 of them, so we multiply by 2, add everything together. We get the formula mass for calcium chloride is 110.98 atomic mass units. Now, Why do we call this a formula mass and not a molecular mass? Well, the reason why is because calcium chloride is not molecular, right? It's actually an ionic compound. The distinction for what makes a compound molecular and which makes one non-molecular or ionic we'll cover in sections 6 and 7 of this chapter. But the main distinction is just to look, if you were to actually look into the structure, for example, if we look at sodium chloride also is a non-molecular compound. It's an ionic compound. If we look at this, nowhere do we see a grouping of the atoms together into a cluster to form a molecule, right? So this is an example of an extended lattice structure, or what we call a non-molecular compound. So we would call, if we added up the masses for sodium and chlorine in our formula, we would call this the formula mass. If we were to look at a molecule, say for example H2O, water is a molecular compound, right? We would add that up as the mass of oxygen plus 2 times the mass of hydrogen, and we would call that the molecular mass. That's all there is to it. So in a previous slide we mentioned that the number associated with a single atom, right, the mass of a single atom, and the mass of 6.022 times 10 to the 23rd atoms gives the same number, right, but in different units. So we want to address the question now, why are these numbers the same? Well, they're not the same by accident. It's based on the way we defined mass. All of the masses that you see in the periodic table are based on this definition right here, based on the value measured for the carbon-12 isotope. Without a measurement, we simply define 12 atomic mass units to be the mass of a single carbon-12 atom, whatever that mass is. All right, so we actually need to measure what that is. We can use a special device called a mass spectrometer for doing it. We'll describe that in more detail later. When we measure the mass of a single carbon-12 atom, it happens to be this value in grams. So we can make this assertion. We define 12 atomic mass units to be this number of grams, right? Now, if we have exactly 12 grams of carbon-12, not something we weighed out or measured, but assume we have exactly 12 grams of carbon-12. Look at what we've done here. We've made these numbers identical, right? And now we want to address the question, well, we know the mass for a single carbon-12 atom. If we take that value and multiply it times X atoms, we will get a sum mass, right? So if we write this equation, essentially what we're asking is, can we figure out how many carbon-12 atoms we need if we added them all up to give us exactly 12 grams? Well, as you can see, from this measured value right here, we can calculate what X is. Oh, look at this number. It looks a lot like this one. That's no accident. This is how we define what we call a mole. A mole of anything, right, is defined, this number is defined from asking the question, how many carbon-12 isotope atoms are in exactly 12 grams of carbon? That's where this number comes from. If we count out the same number of atoms here, not just for carbon-12, but for potassium, we're guaranteed to get 39.0983 grams for 1 mole of potassium atoms. All right, so all these numbers are going to be the same. If we look at rubidium, which is right underneath potassium in the periodic table, if you look at it, that atomic mass number, 85.4678, is the value in atomic mass units for an average rubidium atom mass. It's also the number in grams for 1 mole of rubidium atoms, or 6.022 times 10 to the 23rd rubidium atoms. Okay? That's all there is to it. Let's move on to the next thing, which is to deal with why, if you look in the periodic table, when you look at the atomic mass of carbon, you see 12.01 and not 12.00? Well, the answer is if your carbon was a pure carbon-12 isotope, you would get 12 point, actually to an infinite number of significant figures, because that's how we've defined the mass for carbon, right? As 12 atomic mass units. So it's different because a carbon is not pure in terms of different, it has different isotopes, right? If you picked out 100 different carbon atoms, roughly 99 times out of 100, you would pick out a carbon-12 isotope. Roughly 1 time out of 100, you pick out a carbon-13 isotope. Okay, these are the actual abundances. And so when you calculate the average atomic mass of carbon, we calculate what's called the mass-weighted average, right? So we write here the abundance of the carbon-12 isotope multiplied by its mass, which is exactly 12 atomic mass units, and we add to that the fractional abundance of the carbon-13 isotope. Now look, carbon-13 is not exactly 13 atomic mass units. It weighs a little bit more. Right? It's only for carbon-12 where this thing is defined to be exactly 12. When we add these all together, we end up keeping track of significant figures here, right? We'd round to 12.01 atomic mass units. That's exactly what you have in the periodic table, right? So this is called a mass-weighted average, and it's analogous to this calculation, which you might be a little more familiar with. Say you had 4 people. 3 of them were big at 240 pounds, and 1 was small at 120 pounds, and you wanted to ask the question, what's the average weight of an individual in this set of 4 people, right? Well, how would you do the calculation, right? Well, you've got 75% are big people, right? Or 3/4 times 240, and we add that to 25%, or 1/4 times 120, right? It's analogous to what we've done up here, right? We add everything up and we get 210 pounds on average. So this again is another example of a mass-weighted average. Okay, so to complete this section, let's address this question, right? How does one measure the mass of a single atom or molecule? Well, I've already mentioned it. It's in a special device called a mass spectrometer. But I want you to think a little bit about this, right? So, first of all, we simply can't weigh out the mass of a single atom or molecule. Why? Because the force of gravity is too feeble, and that's the way we measure things on typical mass balances. And the very best that we can do is roughly 10 to the minus 4 grams. Okay, very, very expensive and very sophisticated instruments, we can probably get to 10 to minus 5 grams. But anything that you're going to work on in the laboratory, 10 to the minus 4 grams is about as good as you're going to get. And it's really as a consequence of how feeble the gravitational force is. Now, if you think about it, we've already told you that the electromagnetic force is roughly 10 to the 30th times stronger than the gravitational force. So I want you to take a moment, take this value of around 10 to the minus 4 grams, which is about as good as you can measure with gravity, and take that value and multiply by 10 to the minus 30th, and you should get 10 to the minus 34 grams, right? Now, I want you to take a look at the digits here, right? So this is 1 times 10 to the minus 4th. This is 10 to the minus 25th, 26, 27, 28, 29, 30, 31, 32, 33. So this value is actually determined by using the electromagnetic force instead of the gravitational force. I hope you can see that. That's why we're able to get so many significant figures. The uncertainty in this number is in this too. All of these other numbers are well known, and this is an example of a measurement that's very, very precise because we have a great number of significant figures here. So again, how is this done? Well, it's done using the electromagnetic force. If you recall J.J. Thomson's experiment, right, where he was able to measure the mass to charge ratio of the electron and defined that cathode rays are actually electrons, right, and that have negative charge. He did this by bending the cathode rays or electrons in the presence of an electromagnetic field, right? Any moving charged particle generates a magnetic field and will interact with another magnetic field that you put in the path of the beam. So the mass spectrometer essentially works on the same principle. So here's a picture of it. All right, I want you to focus on two things right now. One is this entrance slit into this device, which we call the mass spectrometer. Here we inject our sample, and inside this device we have a high vacuum, so very, very little air or gases in here. The second thing I want you to draw your attention to is this little thing here, which is a detector. This detects any positive ion that hits it. Okay? So, what's the fate of our sample? If we have, in this case, a sample of molecular chlorine, all right, chlorine is a gas consisting of chlorine molecules. Each molecule consists of 2 chlorine atoms that are stuck together, right? So we take our chlorine gas, we inject it into the mass spectrometer, and the first thing that it hits is this a path between a heated filament and a positively charged electrode. So we heat up this filament and give it a negative voltage, and on the other side here on this grid we give it a positive voltage. Two things happen when we heat up this filament. As you've ever seen a coil of wire that you run a voltage through, it heats up and it emits light. Well, another thing can happen as well. It'll actually, the kinetic energy of the electrons as they're moving through here, move fast enough that they can achieve what escape velocity. Essentially, they can break through the binding force that's binding the electrons to the atoms of the metal. And so electrons can escape and move towards this positively charged grid. Right? So as our chlorine molecules are passing through here, what it's passing through here is a stream of very fast moving electrons going from this point to this point. Right? So the electrons are colliding with the chlorine molecules. So let's describe, using a chemical reaction equation, what happens here. So you haven't seen chemical reactions yet, but basically what we have on the left side we call reactants. These are the things that are colliding or combining. So we have electrons that are colliding with our chlorine molecules. We have an arrow, which means reaction path, and here we have products of the reaction. That is, these things are transforming to these things. So what's happening is that the electrons are moving so rapidly that when they collide with a chlorine molecule, one thing that can happen is that it can knock another electron out of the chlorine molecule. So you have the original electron that you started with, and you add another one. So we have 2 electrons as product. One of them came from this chlorine molecule. Molecules are electrically neutral, so if you remove an electron, a negatively charged particle, from the chlorine molecule, what you're left behind is a molecule that has a positive charge. That's called a molecular ion. There's another fate that's also possible. The electrons can smack the chlorine molecule so violently that it breaks the bond between the 2 chlorine atoms to form 2 free chlorine atoms. When that happens, the chlorine atoms again can be struck by electrons to form a chlorine ion. Okay, so there's 2 possible ions at this point. One are atomic ions and the other are molecular ions. Alright, so these molecular ions then stream on, are accelerated through a grid here, right? And then one particular path is skimmed off, as all of these ions, as they come through, pass through a slit to define a molecular beam. And in the absence of a magnet, what would happen to the molecular beam? Well, it would just keep going straight, right? But because we have now formed ions, and charged particles that move have a magnetic field, they can interact with a magnetic field. So what we're going to do is we're going to place in the path of the beam of our molecular ions a magnet. And at zero magnetic field strength, there'll be no deflection. But as we increase the magnetic field of the magnet, we're going to start to bend the path of the molecular ions, right? At a given magnetic field strength, the light ones are going to be turned the most. The heavy ones, the least. So what we do is this. No magnetic field strength, no bending. We eventually scan our magnetic field strength so that we turn the beam so that the lightest component passes through a slit and then is detected. Okay? Then, if we increase the magnetic field strength, these lighter ions no longer pass through the slit and are detected. Nothing is detected, right? Until we increase the magnetic field strength enough that this one, the 37Cl+, which is a little heavier, finally is bent enough to pass through the slit and then becomes detected. So essentially what you do is you put your chlorine sample through here, you scan the magnetic field slowly, and you detect peaks. Each peak corresponds to a molecular ion. So you'll end up with a graph that looks like this. Plotted on this axis initially would be magnetic field strength. So this would be low magnetic field strength, this would be high magnetic field strength, and you're scanning the magnetic field. You see nothing, 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 and all of a sudden you see a peak. Then you scan the magnetic field higher, and then this goes away, and you see nothing. You scan to a higher magnetic field, all of a sudden you see a second peak right here. You scan further, it goes away, and you keep scanning, and then you see 3 more peaks, all right? Now, we're not plotting magnetic field strength here. We instead plot the mass to charge ratio. So how do we get this? Well, we calibrate the mass spectrometer by first putting in there a pure sample of the carbon-12 isotope. Carbon-12 is going to come off at a certain magnetic field strength, and we call that mass to charge ratio 12, right? We call it 12 by definition, so that's off the scale. That would be way out here, right? Then we put in our chlorine, right? And using this scale then, we can see that the first peak comes off at a mass to charge ratio of 35 relative to the carbon-12 isotope. Well, that has to be the chlorine-35 isotope. We see nothing at 36. The next peak we see is 2 atomic mass units higher, exactly right at 37. Right? So we can identify what these two are. Now, these two peak heights describe the relative amounts. In the beam, we have roughly 3 times as much chlorine-35 as we do chlorine-37. So this also provides you with fractional abundance information, which is what we need to calculate molecular weights. Now, what about these other 3 peaks? Well, they're much higher. The next peak is at a mass to charge ratio of 70. Well, if you take 2 chlorine-35 isotopes and you add them together, you get 70. So this corresponds to the molecular ion. This is a Cl2 molecule with 1 electron removed, right? The atomic mass is 70. So this one shows up here. The next one is at 72. So this must be due to molecules that have a chlorine-35 isotope with a chlorine-37 isotope. And then the last molecular ion has a mass to charge ratio of 74. That must be a molecule consisting of 2 chlorine-37 isotopes that are attached together. Okay? So this is exactly how we experimentally measure the mass of any single atom or any single molecule that we want. And all of the tabulated data in the periodic table reflects mass-weighted averages that are determined from the fractional abundances of our components measured in a mass spectrometer.